is tweeted a picture where it says Vadi.
Ah,
Cool. It's Vadi.
Okay, we're up.
Okay. So I'll just reset the timer. You do, Trevor?
Oh, sure, yeah. Or go ahead. You've been very patient.
so, hi everybody after lunch.
I'll speed up.
I guess many people already attended the previous talk about PLC-Fix, and now Chris and Roman will show how you can use PLC-Fix at the Eve platform to have a pretty flexible Industry 4.0 deployments. So, thank you.
Yeah, hi, thank you for that. Welcome. I'm happy that after lunch, still there are quite a number of people here. So, first of all, maybe I didn't bore you all with a talk before that. And yeah, now we're going to talk about doing some things, showing you a little demo of PLC4X in action. And then Roman's going to take over and he's going to take the demo into the cloud and scale it. Yeah, so. Well, this is sort of the same slide I had in the last talk, but for those who haven't been here before, I'll just speed up a little. My name is Christopher Ditz. I work for a company called CodeCentric, and sort of all of my free time goes into multiple Apache projects. I'm the son of an electrical engineer, and that's what sort of creates the bridge to this industry topic, because I have to admit, at my company, only very few IT people are really interested in hardware. They're more into the cloud, and well, I have to admit, I like hardware. I like it when it clicks. I like it when things break. If you want to follow all the details, I usually tweet quite a bit more on my personal account than on the PLC4X official account, but feel free.
Yeah, quick introduction for myself, for those of you who I haven't met, there's quite a few I have. So my name is Roman. I actually have, my own company right now that I, founded with a few friends of mine out of Silicon Valley. I used to be at Sun Microsystems, building operating systems. We had one that, unfortunately didn't really survive. I'm doing quite a bit of, different things at ISF and also tweeting at this handle.
So, as mentioned before, currently everybody is talking about Industry 4.0. Nobody really knows what they usually understand under that topic, but to boil it down, it's sort of every time it's just IoT connectivity, cloud technology, big data, and machine learning. That sort of sums it up. And the problem with that is that sort of, all of these topics are completely new to the entire industry, both the customers as the established vendors. And there's almost no know-how on this available at the moment. If I went to some company and said, hey, come on, set up a cloud, well, they would just run away screaming because they wouldn't know where to start. There is no knowledge on how to build applications. There is no information on or knowledge on how to run and maintain these sort of applications. And the funny thing is they all want cloud solutions, but they also don't really have an idea what to do with the cloud. So that's sort of a real big problem. As I mentioned before, 2018, I was doing a lot of traveling, talking to companies, and they all wanted to do Industry 4.0, but they usually never had an idea what to do. They just wanted to collect data and were praying that they would have a good idea what to do with the data later on. So what's the problem with that? Well, we built all of that stuff. That's mostly it's all stuff that sort of was built by the open source community. Well, we have all the know-how you need for building such an application. For us, sort of setting up some cloud system is usually sort of just an exercise of a few minutes. Well, for me it's not, but for him probably. But the problem is that we just can't communicate with their toys. Their protocols are usually unknown to us. Only very little fragment of industry hardware is sort of able to sort of communicate in protocols we know. I think usually it's there are some sensors that sort of broadcast information with MQTT, but I think MQTT is sort of the only IoT protocol the industry really knows. There are a lot of networking and compliance constraints. I mentioned that, for example, the security is a very big issue. Well, if I sort of break into some software system today, that is bad, but it's sort of not as bad as if I really sort of break a power plant, because that can hurt a lot of people. And there's a huge focus on the Windows environment. For example, I had to set up a Windows 7 Service Pack 0 32-bit virtual machine to run the state-of-the-art industry software 2 years ago. So just getting Windows 7 32-bit and updating it, so you're already screwed. As soon as Service Pack 1 was on it, you're lost. Yeah, and then even if we built something, it's a real problem how to really scale what we did. I mentioned in my last talk we had a project where we wanted to collect data, a lot of data on a lot of machines. So I think it wouldn't have been a problem for a normal engineer to set up something that gets data from one machine, but setting up to collect data on 26,000 PLCs, well, that's a totally different thing we're talking about. You have to maintain a complete zoo of virtual machines for collecting all that data for processing it. That's a huge problem, and that hasn't been solved. So in order to talk to the machines, well, that's what PLC4X is all about. PLC4X is a set of libraries for communicating with industrial programmable logic controllers, using all of this variety of protocols with a shared API. So what happened in the end of the 90s, where who of you worked on relational databases in the late 90s? So that was a huge pain, writing a piece of software for one database and switching to another vendor, wasn't it? And so then all of a sudden came JDBC. So that solved sort of most of the problems. And that's what we're trying to do now. We're trying to sort of build an API that allows communicating with industrial controllers in a unified way. And I think we're doing quite a good job with that. We mentioned a variety of protocols. Let's say those are, I'd say, not even 1% of the industrial protocols out there. But it's sort of the fragment that sort of you would be able to sort of, a gut feeling would say sort of you should be able to communicate with about 95% of the PLCs out there. You should probably be able to communicate with one of these protocols. The green ones are the ones we're sort of finished implementing. The yellow ones are the ones we're currently working on, and the red ones are the ones we have sort of in the pipeline. So expect us to sort of have green checks on a lot of the orange ones in the next few months, and probably the red ones will become yellow, and there will be a really big list of ones to follow. We also built integration modules, so we can easily integrate software into other frameworks, mainly Calcite, Camel, Agent, and one that's particularly interesting is Kafka Connect, because if we're talking about scale, that's one of the adapters that allows sort of the biggest scale deployment. We've just finished a module for Logstash, and I'm hoping to finish the NiFi integration if I get my hands on one of the NiFi guys here at the conference. I think I'm going to pay him a few beers and probably will get this off the ground. In the near future, we'll hopefully have integration for Minute and Eclipse Cura and Edgex Foundry. OpenHub is sort of something that's been asked quite a bit, but yeah, let's hope somebody is interested in helping out on this sector. So, as I promised in the last talk, I'm going to show you a little demo. So you can, if it's silent, you hear it clicking? Yeah, so this is a a normal off-the-shelf S7 PLC, and it's running a program. And it thinks it's in control of a machine that sorts boxes. I think I had that running. So this is what the machine actually thinks it's doing. So it's a simulation that sort of grabs the digital outputs down here, and those control the conveyor belts. And you can see those little beams here, those light beams. So whenever one of those is triggered, a digital input on the PLC is set. So I could just take this and connect it to the real version of that machine, and it wouldn't even notice. So this is sort of my setup, because I always hate traveling with that machine. It's sort of just getting through check-in, and you always have excess weight. It just sucks. So just assume the PLC is just doing its work, and it's sort of thinking to sort boxes. Yeah, that's all right. So now I have to, as you want to see something, that's the one. Over here, that's one of our example applications we have in that. Yeah. So if you check out the PLC for X project, underneath the PLC for J, we have examples, and the one I'm going to run is the Hello Storage Elasticsearch. And what that does, it sort of spins up a single node Elasticsearch node, creates some indices in it, and starts collecting data from the PLC, namely the values of the inputs, the conveyor states. So just let me fire that up. And I think that one is the right one, is that? I just can't read it. Julian? Or is it elastic?
Yep.
That's the, yep. Okay. How was the presentation of it? Sort of you. Do you know where? Can you guide me where it is? Because I have to stand here. Huh?
No, it's not in there. Just type double shift.
Do you know the key shortcut for
Shift
presentation?
three left and just presentation mode. You go and check it.
Oh, yeah, it's presentation mode on this screen.
Yeah, that's fine.
Yeah, well, okay. So up here we're getting a connection to, no, we're using Apache Agent. So I mentioned Apache Agent being one of the modules we have integration modules for. And what's happening here is we're using sort of the PLC connection adapter and passing in a connection string. And what we get as a result is a PLC adapter, a PLC connection adapter. And here we're sort of creating a Boolean list supplier. So it's sort of, Agent is a streaming framework. I think the last talk of the day, Julian will be talking a little bit on Agent. So what it does, it creates a stream of Boolean lists. And we're currently setting it up to sort of every 100 milliseconds to pull one set of Booleans. We're then mapping this, we're translating this into some sensible information that we want to dump into the database, and sort of sending it to the factory data index. So we're doing two things on this. It's factory data. It's sort of just the raw data we're pumping into the database. And down here, we're sort of creating a second stream from the same input that sort of does some pre-processing. Yeah. And, well, after sort of, in the end, I'm just sort of printing it on the screen. to see what's been dumped. And in order to run things, all I have to do is sort of submit this data stream to the runtime. So now all of my windows have become very, very big. Okay. So, where's the debug? There. Is that? G. Ah, it was the first one. So, okay, it's already running, and you can see here that's sort of the print line at the end. It's just sort of dumping what it's writing into the database. So now I'll just, in order to see something, I'm just going to start Kibana. So that's going to connect to that single node Elasticsearch node that we just started. And we should hopefully see some cool chart. I think I have to pull that over a little. Yeah. So you can see here it's sort of just showing the distribution of large and small boxes. So small boxes are the blue, and the green ones are the large boxes. And what we're currently doing, we're just sort of just polling data from the PLC, processing it and dumping it in some Elasticsearch cluster. Well, the cluster is just size 1 at the moment. The funny thing is, for this, with a typical industry provider, you would probably have to sort of invest 50 to 60,000 euros. And that was sort of just starting an example, and sort of configuring the dashboard sort of takes 5 minutes. So to just show that. Okay, so what's missing? Well, what we're doing sort of uses tools that's generally unknown to the OT guys, the guys taking care of the industrial hardware. And everything sort of outside of the Windows ecosystem sort of doesn't exist for them. They tend to be totally overwhelmed with when you come to them and tell them, yeah, well, you have to run a Zookeeper, and then you have to run this, and then you have to run that, and then you have to buy, you have to have 20 instances for, and they just thought, oh, gee, in the old times, I just started this one application. And well, all of this modern cloud stuff is just too much for them. Sometimes they're also sort of reaching pension age and sort of are just unwilling to deal with that, especially the ones doing the decisions. And so we need sort of a way for the industry to run and deploy these systems in a simple way. And yeah, and above all, we sort of need to make a product out of this. They just don't work this way, that you sort of give them something to sort of, yeah, here's all the tools, now build it yourself. So they want to sort of buy a box and just run it. And this is where I hand over, because he knows the cloud stuff.
I'm the cloud guy. So let me actually switch the laptop, because this one apparently has a German keyboard, which is super weird.
So should I just?
No, you just, I think we should just do this.
As opposed to, say, Russian keyboards?
Actually, Russian keyboards would be fine, because at least the English layout is the same.
So should I remove that?
Yeah, you can, I mean, or you can just close it, I can put it on top of mine. Yeah. All right, so this is basically, yes. All right, so what Chris was showing is actually pretty amazing, and the kind of tools that we can throw at a problem from the development standpoint are actually very well developed, within our community, right? The industry just doesn't know about them, but when we show up and we should, dazzle them with this amazing array of tools, it typically goes through two stages, right? Stage number one, we demo it, in a setup similar to this. Maybe we demo it in a setup that's, at a factory, and then everybody's very impressed, and we're promising to save, a lot of money. And then people typically ask you like, okay, well, awesome. Two questions. First of all, I have factories all over the world. Second of all, in each of these factories, there's not just a single one of those PLCs, but there's basically hundreds of these PLCs. So how do I do it? What do I do? And this is where, good news is that even companies like Siemens are now thinking about this problem space, right? So the way people typically do it is by adding yet another piece of equipment to the factory floor. And I actually have one right here, which I'm, sort of hoping to use for this demo. This is called an industrial PC. Actually, it used to be called an industrial PC. Nowadays, it's most of the time it's called industrial IoT gateway. So this one is actually made by Siemens. Now, interestingly enough, if you look at this box, it has no industrial hookups whatsoever. There is no RS-232, there is no Modbus, there is no CAN bus, there's only USBs. Ethernets, well, they're not really Ethernets, they're basically Profinets, but it's sort of the standard on top of the Ethernet, and that's it. So the purpose in life for this box is to basically make this device, which also has an Ethernet or Profinet, essentially cloud ready, or sort of be cloud native, right? So typically what you would do at a factory, you would have these types of devices, daisy chained, or maybe sort of chained through some kind of a network gear, and essentially routed to one of these boxes. So one of these boxes can actually gather data and sort of do something with that data in the cloud. So then the question, of course, becomes, okay, now we have these boxes, so we need to basically take what Chris just demoed to you and essentially ship on a whole bunch of these boxes at factories around the world, and update the software, because apparently open source is really good at throwing new versions at us. So how do we do this? And if you ask that question, the first thing that comes to mind is that we actually used to have that problem in IT, right? We used to have servers in big dark rooms, and we used to treat them as pets, and we configured every single one of them. And when we had to solve an application, yes, okay, awesome, yes, that's even better. When we basically had to ship an application to them, a special dude was about to configure that application, but we kind of solved it in the cloud, right? So basically, what does it mean in the cloud? In the cloud, it means that you package everything as a container. You sort of use DevOps, practices for managing what's inside that container and how it gets deployed. And nowadays, there's no question that for scaling, if you really wanted to be run, across machines upon machines upon machines, you use something like Kubernetes. So let's try to sort of replicate, these practices, because we're sort of in this mode of getting the best practices of IT into OT, as Chris said, with the demo that he was doing. So I basically literally need to take his laptop and ship to a whole bunch of these devices, right? Well, after all, that's what Docker was invented for. So I actually contributed a few things to the PLC4X project. One of them is this Docker file. And how many of you are familiar with Docker? Can you raise your hands? Okay, good. So at least I don't have to explain the basics. So basically, it's a multi-stage Docker build. A couple of things I will be pointing out that I think are interesting is that, there's all sorts of things that we need to do to build the bits, right? Java bits, C bits, all of that, right? So this is how it's done. We run Maven here, and that's all pretty good. But here, something interesting is happening. So Java has always gotten this bad reputation for being huge, and rightfully so. But starting from about OpenJDK 10, you can now optimize the size of your JRE, which I highly recommend to do if you're doing containers, for your Java. So this is what we're doing here. So basically, everything that you do in containers, by the way, has to be based on Alpine Linux, because if you're not using Alpine Linux in your container, you're not doing containers right. But then you can basically you can basically run this J-Link. It's a new utility that comes to you, courtesy of JDK 11, and essentially sort of add just the modules that you need. I'm cheating a little bit here because I didn't really have too much time. This is the first time Chris and I are doing demo together. You will see a lot of us in follow-up conferences and different ApacheCons, but this is the first time. So I didn't have too much time, so I kind of like threw the well-known set of modules. But even that allowed me to shrink the size of the JDK to just 20 megabytes, which is actually pretty impressive, if you think about it. So I think, I can actually throw this one out, Java Desktop, but for some reason it didn't work with the demo, so I need to figure out, what classes maybe it's using or whatever, right? So this is very useful, and then, in the final container, we're basically just doing, we're exposing the ports. And again, now we're basically going through productization of essentially what Chris has built as a demo and making it really robust, because again, did you know that, for example, that demo basically needs these two ports, being exposed? We probably didn't, because as developers, we don't really talk about things like that, we just assume that everything is available to us. But when you start, throwing that infrastructure onto industrial boxes, like, I was showing you, it actually becomes, pretty important. So that Docker file is actually now checked into PLC4X, so we'll be, using it quite a bit. And with Dockerfile, being there, the next question is, okay, so let's scale it. And of course, people are like, okay, well, now that you have a Docker file and it's sitting in Docker Hub, let's just, run Kubernetes on these boxes and be done with it. And if you watch, the press, a lot of people are trying to basically use Kubernetes, for these types of use cases. There was a famous article, Chick-fil-A is kind of like McDonald's, for those of you who don't know them. They are basically trying to use these types of boxes to essentially doing not industrial use case, but basically inventory management, surveillance, stuff like that. Interestingly enough, just as a quick aside, now that my company is working with Siemens pretty closely, Siemens actually told us that, interestingly enough, even though they mean this box to be deployed in industrial settings, their biggest consumers of these boxes is actually outside of industrial. So these boxes, for example, get sold a lot into airports environments. So when you check in for your airline, it's a box like that that would be, sort of drawing the screen and checking you in. And obviously, Chick-fil-A sort of falls into that same retail space, whatever you want to call it. So then there is, Q-Badge. There's basically a number of attempts. None of them work. So people try to sort of take just what's working in IT and throw it in an environment like that. And in order to appreciate why it doesn't work, let's actually figure out what environment do these boxes exist in, right? And this is just like quick sampling of what my company is dealing with. So these boxes can be behind the dashboard in a car. On this picture, I think we have Dell. These are Dell boxes. It can be like in a small cabinet at a mining site. It can be actually on top of the windmill, producing clean power. It's actually pretty amazing to go up there. So that's what you get when you play with edge computing, and you get to climb one of those. But these boxes actually share a few things in common, right? So in a way, it's very tempting to think about them as little servers because they're quite capable in that sense, right? Every single one of them typically has a few gigabytes worth of RAM, like 2, 4, 8 even, right? So like that's not nothing. I mean, that's definitely not embedded. It has, dozens gigabytes worth of flash. I mean, the CPUs are super modern. So we're definitely not constrained by size. And the reason for that is that as long as you're not constrained by power budget, you can actually buy a really cheap silicon these days. So you're for sure not constrained by money. So it's tempting to look at them and say, like, hey, I used to have a box like that in my data center, 5 years ago. Let's just deploy data center software. But then, and that's sort of, the data center view. But then you kind of think about it and you realize that these boxes actually share a lot with your cell phone, right? Because first of all, they exist in a physical environment that is very hostile. There's absolutely no physical security. I mean, I guess it's pretty difficult to climb that, windmill, but anywhere in like Chick-fil-A or even at the airport, anybody can walk up to those boxes, try to steal them, jack up random USB keys into them. Extract information from them. So that's one. The second one is that they actually exist in a very hostile network environment. So first of all, the networking is absolutely not well designed. And in fact, part of the problem that we've been having this morning is because I now found myself in a network environment that I haven't seen before. And with Project Eve, I'll talk about what it is. With Project Eve, we're basically trying to solve for all those types of network environments, but obviously this one wasn't really on the map yet, so I'll probably happen it tonight. But what we're trying to do is that any kind of network environment that you would throw that box in, the box would actually survive. And that's a really big deal for Kubernetes, because Kubernetes goes completely insane when network partitioning is a norm, not an exception. So Kubernetes actually assumes that most of the time your pods can, talk to the controller, and if they can't, that's a big deal. So you actually kind of need a different approach. I mean, Kubernetes itself is great, but what would be an approach that would take into account all of these challenges of the edge computing look like? And by the way, just like we had a transition from IT sort of to cloud computing, I think we're now looking into a transition from OT or IoT into edge computing. So to me, it's actually a computing paradigm. It's not just an embedded, done a little bit better. So we decided, to create a specialized project for just addressing all of these challenges. And essentially, the project mission in life is very simple. It is literally answering the question of how can a box survive in a challenging environment like what I just described, and at the same time, how can it make shipping Chris's code to that box as easy as possible? The answer is Project Eve, which is an open source project, running on this very box right now. It's an Apache license project, although it uses a lot of bits and pieces like Linux kernel and Zen that are licensed under a variety of different open source licenses, typically GPL or BSD. So the binary distribution is not Apache licensed, but all of the code that's part of Eve is Apache licensed. So Eve basically installs on this box instead of Linux or Windows, right? And essentially completely takes over. We're trying to make sure that Eve gets shrunk so much that we can even potentially start using it as a building block for replacing your BIOS. How many of you have heard about UEFI? Okay, so UEFI is basically a BIOS that exists on every single piece of modern equipment, right? It stands for Universal Extensible Firmware Interface. It's a complete and utter abomination that was, enforced on us by evil corporations. We can do much better, and there's actually great work happening in the Linux community with a project called CoreBoot that tries to replace all of that goo with essentially just a Linux kernel, that your machine basically uses the Linux kernel to set itself up, right? Things like setting up memory and controllers and all of that. That's typically what BIOS does. Linux kernel can actually do a lot of that. Yeah.
Does that mean to run on a separate secure core? Because you've got multi-core chips, so the geek who builds cores uses secure core. That's what people think of as a secure core.
Exactly.
It's locked down, then you run the rest. And you're like,
that's right. That's right. So we're actually trying to integrate Eve with CoreBoot so that it actually gets to be a replacement for your BIOS. Right now, it's just, you can think of it as an operating system. And at the end of the day, we will be running edge containers. And again, that Docker container that I was showing you would totally be an example of an edge container. So edge containers are an extension of Docker containers and OCI specification. So anything that's today available on Docker Hub would totally be an edge container. Using Eve is pretty simple. So basically the DevOps, we call that person Diane the DevOps, uses the Eve controller, and today my company actually produces a closed source, Eve controller. That's how we make money, but we hope that other people will produce open source controllers. We actually have an open source controller, a very simple one in the Eve project itself. And the controller that my company does looks something like this, right? So you basically have, a full sort of view, full visibility into all of your devices. You can kind of see, which devices are here. Here's my Siemens box. That again, because of the networking challenges, haven't been, able to communicate for the past few hours with the controller. But you basically get all of the basic information, all of the adapters, and you can manage it in a pretty flexible way, right? But of course, the key to all of this is this idea of app bundles. And one bundle that I obviously created for this demo was PLC4X demo, which is literally just taking, that Docker container that I showed you and essentially pointing this bundle at that Docker container. So if I click on this bundle, you will see that there is basically an image, PLC4 demo 3 that's actually sitting on Docker Hub. And that's how I can make sure that that actually would be running on this box. So that's kind of what the controller would look like. So let me get, yes. So
Just click in it and then
really?
these should work again.
Oh, really? Okay. So basically, Diane, the DevOps, anybody who wants to deploy a demo like what Chris has just done would be talking to the controller. So controller right now talks, this hybrid API that was inspired by Kubernetes, but we are trying to basically make sure that controllers give you the cloud API that is Kubernetes, right? Because the API is great. I mean, it's the implementation that is challenging on the edge. And then the controller itself basically uses the open API that gets standardized as part of the Eve project. Eve, by the way, is governed by Linux Foundation, and we can have a long discussion in the community track of why it is so. As part of that Linux Foundation project, we also have the API standardized as well. So Eve then runs on all of these boxes. These boxes typically communicate with, either PLCs or, industrial equipment. Sometimes they just drive, like a check-in kiosk at an airport. But Eve essentially is an execution engine, and Eve, by the way, stands for Edge Virtualization Engine, where controller is a scheduler, right? So think of it this way. Eve basically exists at the level of like Docker engine, right? A single sort of Docker running anywhere. And controller exists at the level of Kubernetes, essentially scheduling onto those engines at different factories and different places, right? So as a user of Eve, yes?
I'm going to throw a spanner in the works. Encryption certificates, is it you can solve the
yes. So
in the whole?
Correct. So Eve basically, and unfortunately I don't actually have time to go into deep details, but just to capture a few things that Eve is helping you to solve. So Eve takes security of industrial IoT super seriously so that you don't have to.
It's a hard problem, yeah.
Exactly. So Eve basically does a few things, interestingly enough. So anything within Eve universe basically gets a crypto identity that is rooted in the hardware element of the box. So from that hardware element in the box, you basically get a certificate, a standard X509 certificate derived. There's a lot of policies that you can have, around how key gets rotated and stuff like that. But anything and everything security-wise gets derived, from that on. So to answer, very quickly to answer your questions, yes, security basically is given to you from the get-go. Everything is encrypted, which is interesting because we don't trust anything. So the joke is that Eve is sort of like a botnet, but done by good guys, right? We want to survive in any kind of environment, and we don't want to be subverted. But again, why are we doing it? And maybe that's actually a good point for me to sort of elaborate on why are we doing this. Because the natural tendency in IoT is to do that integration yourself. And typically you screw it up. Because not a single system integration company or a person is an expert in all of the stack. So basically what Eve is doing, and that's actually part of more of a serious, not tongue-in-cheek answer of why it's in Linux Foundation. Eve is basically trying to say like, okay, so let's basically decouple edge containers from all of the infrastructure that needs to be there to be secure, to run edge containers. And in that sense, we're taking a page out of the mobile industry book, where how Apple in US is now running those ads saying like Apple, iOS is the most secure, mobile platform, which is sort of true. They've done a lot, very similar to what we're doing. But interestingly enough, Android is actually in a way may even be considered more secure. So Eve is basically retracing all of the steps, and actually we are reusing a lot of the software from these guys to essentially make sure that security-wise, this box is at least as hard to hack as your mobile phone. I mean, good mobile phone, so either iOS or Android. And then on the application side, just like being an Android or iOS developer, you don't care about any of that. Like you just know that your platform is secure, the platform is managing all of the expectations of your application, and that's where the edge containers, sort of kick in. So with that, again, Eve is trying to answer a lot of the same questions that Android has answered, right? we are taking a lot of inspiration from Android as a platform. As a quick aside, I used to be a long time ago, in a galaxy far away. I used to be on a team that did J2ME, so I'm not making those mistakes. I'm making new mistakes now. So basically, 4 fundamental questions that any platform like that needs to answer. How do you do application and operating system sandboxing? Meaning, how can you make sure that applications don't step on each other and don't corrupt the operating system? How do you do the application bundling? How do you do the app deployment? And what hardware are you supporting? So again, if you look into what Android did as an answer, it sort of made sense in 2004. Now is 2019. We're giving you slightly different answers, but it's basically the very same questions that we answered. So if you're thinking again about, just to recap, if you're thinking about Eve architecture, you basically have this idea of edge containers. It's how you capture the workloads. And now is a good time to ask me, like, Roman, you keep talking about this edge containers stuff. Why can't you just use Docker containers? And like I said, we can. We can. It's fine. Any container on Docker Hub is an edge container by definition. But the problem is that in order to support a lot of use cases that exist in industrial IoT, you actually have to extend pure containers into essentially virtual machines. And when I say it, people go like, well, surely you're not talking about running, old school virtual machine. And I'm like, well, sort of I am. Because if you look into a lot of SCADA software, today it's being run on Windows, wait for it, 95. I'm not joking. I'm serious. And when you're trying to connect that thing to the cloud, the question of how do you install firewall into Windows 95 becomes sort of iffy, because not a lot of companies, including Microsoft, actually support Windows 95 today. Even with Microsoft, you actually have to have a very, very special contract to still be supported, right? So then we're basically saying, like, well, how you do it is you take that, you essentially put it into an edge container, like just capture it, the good old way that VMware used to do with physical to virtual, put it into an edge container, and around that edge container, we will basically build a firewall that is all Eve derived. There's no software that needs to be changed inside the VM. So, and that's actually why we're using the type 1 hypervisor, big reason, because using virtualization tricks, we can make a lot of the magic happen on the other side of the hypervisor, so that all of the VMs running here can be as dumb as they want to be. So a couple of good examples, right? It's like for that prototypical Windows 95, we can emulate a floppy drive. And a lot of the information injection actually happens through the floppy drive. And that's doable. It's not like you can hook up a floppy drive to this guy. Another example is networking. So again, take that same Windows 95 application. So suppose you want to actually hook it up to the VPC, virtual private cloud, I guess, on Amazon. So then it's IPsec. It's not like Windows 95 supports IPsec by default. Like, what do you do? Well, what you do is, you basically give that VM a virtual NIC, a virtual Ethernet adapter, and it just knows to send traffic to it. All of the IPsec decomposing basically happens on the other end of the hypervisor. We're essentially capturing all of the traffic from the virtualized NIC and sending it where it belongs. So what we're trying to do, we're basically trying to bring that use case plus real-time operating systems, because again, these boxes are pretty powerful. But the question then becomes, can you statically partition them to basically have, a portion of your silicon, like 2 cores, maybe given to a WindRiver or something like that, right? And a lot of the other cores, running Chris's demo. And with Eve and edge containers, the answer is yes, we can. And because again, we're running type 1 hypervisor. By the way, today it's Zen. Intel guys are working on integrating Acorn into Eve. Siemens approached us with Jailhouse. It may happen if they pay us a lot. Please do. But type 1 is important to us because for real-time use cases, we cannot trust the Linux kernel scheduler. Now, again, if I say the same at the Linux Plumbers Conference, I basically get to experience a bit of a firestorm. Yes, you can make it sort of real-time, but again, we'd rather rely on the hypervisor. So yeah, so how much time do I have? Five minutes. Okay. So that's kind of about it. I was actually trying to make sure that I can literally, take what Chris developed and just move it to the box, so we don't have to change anything else. Like I said, I mean, we ran into a few challenges in the network environment here, so we'll be debugging it tonight, in the hackathon room. If you're interested, drop by. I can show you how I sort of do it with Eve. And hopefully by tomorrow we'll actually have like a complete transfer of the demo from here to there, so that the Kibana he's running will keep running on his laptop, but all of the collection of data and actual node of the Elasticsearch will be running on this box. And with that, I really would love to leave you with this lovely quote by my childhood hero, Cloud Opinion, on Twitter. I think he's absolutely right. What Chris and PLC4X is doing is awesome, but I think we really, let me put it this way. If we want to hang out in the industry with the people like that, we actually have to turn the industry around. Because you cannot show up in the industry and expect people who are still running around with floppy drives to basically appreciate what you do, but you can if you give them good tools. So what we are trying to do is basically give them tools that are at least as good as what cloud community has developed today. So at some point you don't have to worry about what's the operating system, what's the middleware, how it's all connected together. And Chris was talking about representing different sort of PLC endpoints. One of the things that we, for example, can do on Eve side, and I've been thinking about it again through virtualization, is essentially giving the virtualized representation for the PLC controllers themselves. So when you're running inside of the edge container, you don't have to think about what is the actual model of the controller that I'm talking to. You can actually get the virtualized representation. It's kind of like once you have a hypervisor as your hammer, everything needs to be virtualized. So we'll be doing a lot of that. So thank you so much, and Chris, maybe you can come back so people can ask us questions.
Sure.
So any questions?
Looking at some of the newer hypervisors like iTrack and Gvisor that are geared towards.
So gvisor is definitely an interesting thing for the traditional cloud isolation. It's not a hypervisor that would be useful for what I was telling you about real-time use case and sort of running a traditional Windows. And I think it's actually very important to sort of understand the pros and cons of all of these new technologies, right? So I think the industry is really settled right now on the cloud side, on traditional kind of like public cloud side, on two things, right? First of all, it's all Linux everywhere, with KVM. Like it's done, it's a given, it has happened. And second of all, it's traditional Kubernetes. Now, anything that sort of plugs into that ecosystem, Firecracker and gvisor is great because it sort of enhances that ecosystem. I don't think we can just take that ecosystem and move it to the edge. And again, people have tried, they failed. So that's why Linux Foundation now has LF Edge, where we can learn from each other's mistakes. So yeah, to your question, I get excited about these technologies, but they're not really helpful to me on the sort of in the environment that I'm running.
I already asked a similar question this morning about Yocto, because Yocto is trying to also fill in this gap, like having firmware which is reasonably safe and we are all mature. So how do you think you relate to Yocto? Just a replacement?
Yeah, we're a complete replacement for Yocto. I think Yocto in industrial will be a huge mistake ultimately, and I'll explain why. Because Yocto is really good at building self-contained, single-function, firmware pieces. What we are talking about here is actually yet another cloud. So I think the only useful way to think about edge computing is like you have all of these public clouds, right? Amazon, Google, Microsoft, and from now on you will also have on-prem cloud that's outside of your data center. That's edge computing, right? So there will be a lot of computing that's just not single-purpose, single-function, right? So you will have, machine learning and AI, and we have like customers, trying it in self-driving cars, and this and that. Yocto is not set up to provide you with an opinionated platform to basically do all of its security. So Yocto gives you enough rope to, hang yourself or build something that works, but it just doesn't have as a use case this opinionated platform that in a way constrains you, right? But it does it out of goodness of its heart, not because it hates you.
Go back to networking. So the type of environments, so I don't know industrial, I know retail pretty well, and one of the big differences between sort of cloud computing and server line computing is over there your networks are really tightly constrained non-distributed. If you've got latency, if you've got delay, it's very tight. If you roll it out onto the real world where these are going to be networks are probabilistic, you don't really know whether it's on or off. So in a server, non-distribution, it either works, connects, or it doesn't. Out there in the real world, you get a huge diversity, very big statistics. Who's working on the solution to that? Because as far as I'm concerned,
we are. So let me talk about yet another favorite feature of mine of Eve, which is Eve actually comes with basically built-in SD-WAN. And again, the reason we do it is so that when you run your container, you don't have to ask yourself, how do I do service discovery on something that happens to be 2 NAT boxes away from me? Because again, in a data center, nothing is 2 NAT boxes away from you. It's all sort of a very flat, well-designed, network space. So again, I cannot do it full justice, but just top level how we do it. So we basically use this protocol called Lisp, which has nothing to do with the language and everything to do with location identifier separation protocol. It's an IETF standard. And like I said, remember how I said that everything in the system basically gets a crypto identity associated with it? So every box, every piece of functionality, including the edge containers. So basically with Lisp, we use this really interesting trick. Essentially, Lisp gives you the overlay, and the overlay is driven by IPv6, so you get 128 bits. So we're hijacking that bit space, and we're using hashes of the public key of the entity that you're routing to, and it's all flat, right? Because it's IPv6, we don't care. So we're using the hash of the public key of the entity that you're routing to basically as an IP address. So you're always routing to a crypto identity, and whatever is that you're routing to, you also, of course, encrypt with the public key that you're routing to, which kind of solves 2 issues at once. So first of all, everything is encrypted to the destination, and second of all, the hash of that destination basically is the IP address that never changes within the system. That's why you have to run an overlay. Now, again, your IP address can be behind net boxes and you can move and whatnot, but that address will never change. Any other questions?
Start to build back all your hardware setup for the next one.
Yeah, this is kind of cool. I like it. We need to move it to the hackathon room.
Yeah, getting it through the airport security was a challenge.
Oh yeah, I could say.
Yeah, so I think we're both going to be hanging out around here. So if you've got any other questions, just feel free to come to us. We're more than happy to speak about our babies.
Indeed. Yeah, drop the mic. Drop the key.
And the Siemens box.
And yes, and everything.
Is it safe to go except all the wires?
Well, some of them are actually mine, so there's that.
Which ones?
Black ones. And the guy. Yes.
What's up? Yeah.
Yeah, no, but
Ready for some afternoon coffee.
passively cool, so it's passively cool.
Yeah, 'cause how long is that flight?
Wow. No, but have you touched a Raspberry Pi 3 or 4?
17?
I kind of read that.
That's still a long flight. That's pretty good. That's a good hop. I only flew.
Oh, no worries.
Sure. I think I was 3 in the air, so I'm doing a lot better. How long you in the hemisphere for?
Unbelievable. I gotta ask you guys that
Not
prop.
horrible.
Yeah,
I did
prop.
I did Chicago to Shanghai.
Always mention it.
Well, with Chicago to Shanghai, and it was
I'm gonna take a picture.
30 hours in the air and 48 on the ground, and it broke me. I don't want to travel the rest of the year. I just want to stay at home. I'm lazy.
So I have to get all the cables back in there.
Let's see. It was David, what's your Twitter handle?
Shoot, I'd have to go back and look. I actually don't care.
Well, do you care if I don't tweet at you then?
That's fine.
Okay.
Yeah, and then I have a holler rate. It's under 50 days. This is the USB-C. Okay. So I have an adapter.
Can you just take, I guess, Chris one has one.
Yeah.
Just don't forget to do it back and read better Wi-Fi or whatever.
You tackled me, that's completely
I'll just give you.
Was it quite a good day?
Like you give your own personal.
That doesn't seem right.
I guess those are pretty
All right, guys.
Yeah.
We're hoping so. I mean, it's definitely, it's trending up higher. Yeah. It's been at it for 3 years and then people I saw.
As a my father, it was sort of like a suitcase.
Yeah, how did you get the? That's another.
What's under the copies?
Left side next to the door or something.
Oh, really? So Pulsar, I got it was started as a project. That's been around since 2000. That's been around for a while. So it's been open source. I guess. 3 years, I think. At top level. Yeah. So.
It started 3 years.
Yeah, exactly. So take a picture of this.
Yes. Also, brings it on the ball.
That change. It's just peaceful for more.
Just went back with
That's dead. That's good. At least you get that up frame.
There is. Not too much interest in using phone. Not much.
That's good.
Good not to get into this.
No, we don't start religious books. It's great to hear. It's,
There was their after Dr. John. Oh, I can't help it.
In fact, it's a friend of mine who So.
yeah, exactly. We have our further little rivalries.
That's the best. It's like productive. Basic form.
All right.
Oh,
Yes.
go ahead. You can introduce.
So, hello everybody. It's nice to see so many people here at the IoT Track. Next talk will be from David about how Apache Pulsar can support real-time analytics for IoT applications. So, good.
All right. Thank you very much.
My name is David Karamgard. I work for a company called Streamio. We're one of the primary committers around Apache Pulsar. I'm going to give this talk on how you conduct real-time analytics with Apache Pulsar. So this, one of my coworkers takes a picture, so my boss knows I'm working today. So just a little background here, just to get a reference. How many people have heard of Apache Pulsar and know what it is? I like that. Last conference I got exactly one hand, so I like that. The numbers are trending upward. These are some of the bullet points, a little bit of height, a little bit of, it's a cloud-native messaging platform. It was developed at Yahoo. It's horizontally scalable in terms of topics and storage. It provides message ordering, durability, and delivery guarantees. It supports both queuing and public, so it's more than just a pub sub, it's also queuing as well. And it's basically a messaging system, messaging platform. And it has a decoupled serving and storage layer, which allows, enables some edge development, edge deployment as well. So those of you who are on the earlier talk, they had this interesting device around IoT gateway. It would kind of get deployed on a platform like that, be sort of the target deployment environment. Just, can you hear me? Yes. Well, there you hold up, that's a prop, thank you. So when I mention IoT gateway, that's exactly sort of the computing platform we're talking about. So, great, thank you. So let's first just define what I'm talking about as IoT analytics. There's a lot of different expectations of what it is, but it is not just about loading sensor data into a data lake and then creating predictive analytic models on top of it. I mean, that's obviously one of the crucial pieces of the puzzle, but that's not the entire thing. It's, you don't just suck all your data into data lake or analytics after the fact and say, hey, I've got IoT analytics. No, you don't. IoT analytics requires the ability to ingest, aggregate, and process an endless stream of real-time data coming off a wide variety of sensors out on the edge. It's nonstop. You can't stop it. You can't redo it. The data's coming endlessly, nonstop. You have to be able to process it, and you have to be able to process it closer to the source. It allows you to render real-time decisions out at the edge as well, out at the edge of the network to either optimize operational performance, detect anomalies, do some immediate remediation. It's not only good enough to detect something's going on, then you have to react to it as well to get some value out of it, right? You have all these sensors going on. What's the point of a sensor if you look at the data 3 weeks later and, oh yeah, we should have turned the machine off, at that point in time. It doesn't matter. You want to be able to react to it in real time to make it worthwhile. So what makes IoT analytics different than traditional analytics or different things? In a nutshell, you got more data, high continuous volume data in motion. You're just constantly getting data coming at you from, discrete sources, a time series sort of data. It's more complex. You have to use multiple analytic techniques. It's not just one technique you have to use multiple ones. And you have to do it in a distributed manner, often out on the edge, which is what we're going to cover as well. And then lastly, there's more automation. Again, I spoke about earlier, it's not just being able to identify these anomalous events or these trends, but you have to react to them. So you integrate with operational and business process management systems, and you have to have bidirectional communication both ways. I detect something, I send it to you. You can send something back up to the sensor to activate something, turn it on, turn it off, that sort of thing as well. So what are some of the IoT analytics challenges out there, right? You're dealing with a lot of machine-generated data of discrete observations such as temperature, vibration, pressure, produced at very high rates. So you need an architecture that allows you to quickly identify and react to anomalous events, find that needle in a haystack, proverbial needle in a haystack. And you also want to reduce the volume of data you send back to the data lake. There's no point in sending millions of the same exact temperature measurement back in the same sensor. It's not very interesting. And you want to send all that data in, store it, process it. It introduces latency, it introduces cost. It's something that you really don't want to have in your architecture for IoT analytics specifically. So in this talk, I'm going to present a solution around Apache Pulsar functions that distributes the analytics processing across all tiers of the IoT data ingestion pipeline, allows you to sort of solve some of these challenges with IoT analytics. So in my mind, this is the conceptual IoT ingestion pipeline as well. So you have your IoT devices and sensors out on the edge. Those are the very level sensors out there at the far edge. And then at the first layer is again, the IoT gateways that was some kind of hold that up earlier. What those are, they're connected to the network. They're very small profile devices. Usually have 4 to 8 gigs of RAM, a very limited disk, if any. Their biggest piece in the network is that they connect you from the MQTT world or the closed network world of your plant, plant floor operations out to the internet. They allow you to take that data and move it out to the internet to the data collection tier, where you start doing it queues and topics. You have longer sort of retention. Then you have a messaging layer, and then from there you can have sort of your real-time stream, where you have your traditional analytics happening out with like Flink, Storm, Spark Streaming. You can have the sort of real-time processing all these queues, but you have high-volume data. And then you also have longer-term storage. That's where you do your remote analytics as well. And we have a feature with Apache Pulsar that does SQL You can run SQL queries against it as well. And my coworker Jerry Pang, who's here supporting me, is going to give a talk on that, how you can do queries on the data all within Apache Pulsar. So the first two layers, you're just worried about data transport, getting the data from point A to point B. But we can also see that we can also start doing some filtering and aggregation out there at the edge as well. You can start doing some analytics, also starting to do analytics on the edge. Traditionally, it will start at this layer. Once it lands, you've gotten the data all the way in. We want to do it much sooner. We want to do it much closer to the edge. That's the whole point of having it as close to the edge as possible. So with Pulsar and Pulsar functions, we're pushing that processing back out towards the IoT gateway devices. So that's the problem statement. Let's do a little bit of background on Apache Pulsar functions. Are people familiar with Apache Pulsar functions? Are people that have heard about Apache Pulsar? What they are basically is just a flexible serverless computing framework that allows you to execute user-defined code and functions that process on the data as it comes in event by event. So those of you familiar with AWS Lambdas, for example, the data comes in, you write your own code in your own particular language that you like. There's no framework around it. It's just free-flowing, Java code, Python code. We have Go code as well, we're now supporting as well. Allow you to just have this event-based, so you can subscribe to multiple input topics. A function gets executed when an event comes in, and you can publish one or more output topics. They're implemented as simple methods, so you can just leverage existing libraries as well, which we'll show you in this talk is one of the keys. If you have existing investments in Python code or Java code that you've already written or exist out there in open source, you can leverage them inside of Pulsar functions. They execute against every single event that's published in that specific topic, so you can sort of have, and you can chain them together, so you can have multiple functions, do some aggregations, filtering, that sort of thing, transformation, enrichment, and then finally do the analytics on it as well. You can chain them together as you want. And like I just mentioned there, you can do dynamic filtering, transformation, routing, analytics as well. And they can run anywhere that a JVM can run, including edge devices like the IoT gateway. So these things can actually be edged out right when you're pointing the sensor data, you can actually measure each individual event. Some of the interesting things you can do with these are just some of the different canonical use cases you have with Pulsar functions as well. So you can do some record-based filtering, basic enrichment. One record comes in, you process it, one or more records come out. Things like lookups, range normalization, field extraction, basic scoring, things like that you can do with a simple Pulsar function. We also have stateful functions as well, so you can do more interesting things there in the second row. Things like cumulative aggregations and filterings, analytics as well. So you can do like mins, max, cumulative average, running average, that's 5-minute window, tumbling window, that sort of thing. So what's my temperature of the past 5 minutes? What's the average temperature today? That sort of thing for a sensor, for example. And then lastly, you can also do window-based aggregation as well as and analytics. So you can do moving averages and pattern detection as well. All these capabilities are brought to you, the sort of things you can do with Pulsar functions. Now, the $50 word slides here, right? Distributed probabilistic analytics with Pulsar functions. I just tried to get the maximum word score in Scrabble, and that's what I came up with. But realistically, what that means, let's break that down a little bit. Obviously, distributed is we're going to do it out on the edge. We're going to do all these different IoT devices. We're going to do the same thing. We're going to have multiple instances of the same functions running across all our different IoT gateways. So now we're focused on what's probabilistic analytics, right, or analysis. So oftentimes, you don't want to get an approximate, approximate value is good enough. You don't need to get a precise measurement of something. All you need is an approximation. Good case in point is like, how many people have visited right now? What's the total page visit for Google? As soon as you gather all data and calculate that, by the time you calculate, the numbers change. And you do it again and again and again. You really just need to know to the nearest 1,000, 10,000, 100,000, something like that. Or if you're looking at temperatures, you don't need to know it's 98.6217458. You just need to know it's 98, 95, 96, something like that. You're just getting a rough estimate of that. So probabilistic algorithms have a way of allow you to give you approximate values when an event off an event stream or event store is just too large to store in memory, or the data is just moving too fast to process it. You just want to do some sampling to get some data on that. So instead of requiring to keep all that data on hand, somewhere, you can obviously use these algorithms that require only a few kilobytes of data. So why only a few kilobytes? Why is that critical in this use case? Well, because we're back at the IoT gateway. We're out on the edge. We have limited space. We have limited data to use. We're only going to, we're not going to have megabytes and gigabytes of data to use. We got kilobytes. And you can do all these sort of techniques with just a few kilobytes of data. So all of these? So these algorithms have been around for a while. They were developed in the late 1970s, early 1980s. They're just kind of coming back into the heyday because they're more interesting now. You have event streaming, real-time streaming, and data volume that makes them useful. But underneath the covers, the central theme to all these things is this concept called data sketches, right? And they're just they only require enough data to make an estimation of the proper answer, so you can size them properly. Right? Typically, sketches are implemented as bit arrays or maps, so therefore they only need the kilobytes of memory that I mentioned. They only need a very, very small footprint, making them ideal for these resource-constrained environments. And sketching algorithms also need to see each incoming data item only once, so you never have to replay the data. I think you do traditional analytics or queries, you do a sort by and a join, you have to scan that data table once or twice, rejoin it, do it multiple times, you have to keep it on hand. With these, you see the event once, that's enough. That's all I need to do with it, and I can do this with the kilobytes worth of memory. So some of the properties they allow you to have is they have configurable accuracy. So once you can predetermine how accurate you want it to be based on the size. So if they're sized correctly, they can be 100% accurate to the precision that you want. And the error rate is inversely proportional to the size of the sketch. So if you want to, the more memory you have to give, the more accuracy you can have, the less to reduce the error rate, but you can make that trade-off yourself based on how much memory you have available to you within your IoT gateway and those sort of devices that you want to do this analysis on. Next thing is fixed memory utilization. So you're not going to have the dreaded out-of-memory error. You're not going to have a resource hog out there crashing your entire IoT gateway, all your sensor data that's flowing in. You're not going to have one bad actor out there pushing your device and bringing your entire network down. So it's a very critical thing. You size the sketch ahead of time, and the memory cost is always known in advance, and it never changes. And lastly, and most importantly, it allows non-additive operations to be additive. So what does that mean? So those of you who are familiar with the Hadoop world, and the hello world, or the hello world of that space is the word count. You do all the different counts, how many times the word appear, all the different segments, you sum them up together, that's your accurate answer. It's the exact same concept here with sketches. So if I do a sketch on this IoT gateway and this one and this one and this one, if I add them all, funnel to the same place and do the aggregation, I can just add those up, and it's as if I did that same stream of data in one place, I can sum them up. So it allows you to do it in a distributed, parallel manner. So it's a big win for us when you have thousands and thousands of sensors across that sort of thing. So here's sort of an example of what a sketch is, right? This is just sort of show you what I mean by sketches and a visual representation of that. See, as the data comes flowing in, you don't need all the data right away. You don't need all the data to make a decision, but over time, your picture forms more accurately what you're looking at here. So ask yourself, at what point do you understand what this picture is? Yeah. You had enough of the keys, so you have that's an idea of a sketch. Okay, I know what it is. All the rest is just all this extra data after the point is just noise. You don't need it. I can make that decision quickly. So I'm going to cover just a couple types of sketches, but there's several different families of sketches that can all be done in the same way. They're different types. I apologize for the font on this. I tried to squeeze them all in.